Okay, so we will talk about force analysis, as we have said. So when we mean force analysis, what do we do? First of all, when we are doing engineering design, what is the procedure? Well, at least engineering design for machines, let's say. We first start from kinematics, just as we have done in our class. Kinematics is important. You have position, velocity, accelerations, etc. Okay, this has to be determined what kind of motion you are generating, and then you have to. Kinematics has nothing to do with the forces, by the way. We can design it totally without the forces. Then you have to calculate the forces. Okay. Well, let's say this is the design procedure. Well, you calculate the forces. You can now calculate the forces after solving the kinematics if the external forces are given. But there is something missing. After that, after the forces are calculated, you can design the members. The members, let's say, and let's say joints, etc. Okay. That is, you decide what kind of material you are going to be using, what will be the thickness of your member, what will be the thickness of your joint, etc. All these things have to be determined in the final analysis because you require the forces. This requires, you know, the strength analysis, etc. Okay. Well, of course, this is the logical procedure, but there is a problem here. You can guess that. If you want to calculate the forces, this requires some knowledge of mass and inertia, isn't it? Because why? Summation of forces is equal to ma, and also summation of moments is equal to I alpha, as you know. So without these quantities, I mean, let's say since we calculate the forces in the second step, in that step we don't know the masses or the inertias, right? Because we haven't designed the numbers yet. They are just very abstract objects. So what do we do? But M and I not known, let's say. This is M. In the beginning. Now, well, in the final case, we will do this, but so how do we deal with this? We do some kind of iterative way. Well, we overcome this by the following approach. The so-called, it will be an approximate thing, but we first do static force analysis. What does this mean? Static force analysis means you either assume that the accelerations are zero or very close to zero. The summation of forces is zero. Summation of moments is zero. Okay. And which means that either M is very close to zero or that is I is zero or alpha is. Yeah, the inertia forces are negligible. Okay, that is what we assume, because in the beginning, really, we don't know. So we basically ignore the inertia terms. Okay. So in a way, this approach is approximate. But in the beginning, you need to have a knowledge of forces. So you usually start by static force analysis and then do dynamic analysis, dynamic force analysis. Which is summation of forces is equal to m times a of acceleration of the mass center, as we know, okay? And the summation of moments about the mass center is equal to Ig times alpha. We will see this, okay? Later on. This is the later step. But we will start with static force analysis, okay? And then we will do dynamic force analysis. Probably we will spend something like 3 weeks or something like that for that purpose. Okay, so let's go on. Now, for the force analysis, what the fundamental laws we are using are, as you know, are the Newton's laws of motion, which are familiar to you, I suppose. The first law, the external forces acting on an object, if this is zero, this is the condition. If, I should say if, then you have two possibilities. You either have no motion, or if there is a motion, it is a uniform motion. On a straight line. Okay. If the four external forces acting on an object are zero, then the object either does not move or it moves on a with constant velocity on a straight line. Okay. The second one is the most famous one, as you know. The summation of forces, external forces, is equal to, well, this is the mass times the acceleration of the object. And the third one says that the action equals reaction. A force applied by the ith object on the jth one, for a force like that, there's an equal and opposite force applied by the jth object on the ith one. Okay, that is the forces are reciprocal in a way. So let's keep this in mind, and let's start the static force analysis. Well, this will be for now it will be a review. I will just state very obvious facts. As you know, force is a vector. So it is shown by the arrow on top of it. And vectors have, as you know, both magnitude and direction. And also, one more thing which is important, maybe, they have a point of application. The forces are important. For example, you might have an object in static equilibrium like this, okay? As you see, well, the point of application of the forces F and minus F is here. So the summation of total forces is 0. But actually, in terms of statics, this is equivalent to the following. The same object. I can replace these forces. For example, I can put this minus F here, minus F in this direction, and F in this direction. Okay? Well, this will be in tension, this will be in compression, but still for our case, it is okay. So for statics, that is tension and compression for statics, well, is this kind of the same thing. Of course, we recognize it, but it is more important for the deformable bodies, for strength of materials. For statics, point of application is not that important, but the line of application of forces is important, not the point of application, okay? So in a way, if you have a body like this one, you can have, if this force is applied like this, okay, to this point, for the case of statics, it doesn't matter really. We can replace this force by the following force. Let's say it's the same force, okay? As long as the line of applications are the same, this one and this one are the same, let's say, for statics. Well, if the line of application changes, everything changes because, well, their moment effect is going to change, and that's not acceptable. So again, let's go on reviewing. Let's say that we have a three-dimensional coordinate system, like whatever, doesn't matter. And let's say that we have a force like a three-dimensional force F. And let's say that we have a unit vector in that direction, U. As we know, our force can be decomposed into its rectangular coordinates, fxi. Let me use the unit vectors like underlining them, plus yj. Unit vector, and the unit vector's magnitude, as you know, is 1. Well, it has to do with direction, cosines, etc., etc. I don't want to go into details of these. You probably know these anyway. Well, we usually, at least in this course, deal with two-dimensional cases. So let's review this. Let's say that this is our force. Let's say this is an angle theta. Okay. The force F, let's see, this is X and Y. The force F can be written as its magnitude times the unit vector. Okay. The unit vector is the vector in this direction. But we know that this is the unit vector. From complex numbers that actually we can write it as F times e to the I theta. Okay, this is the unit vector. Or another way of writing this is the phasor notation, F and theta. Okay, F with an angle of theta. As you know, the x component of the force is F cosine theta, and the y component of the force is sine theta. That is, this is the Fx. So forces can be decomposed into their components, and the forces have certain, the so-called moments. Let's say you have a point, and then there is a point of application of a force, like here, the force F. Now, between the point of application of the force and the point O, let's say that there is a vector R. This doesn't have to be perpendicular or anything. It can have an angle of theta in between. The moment of that force about point O is defined as the cross product of R and F. It is the rotation effect of the force with respect to, well, about this point. And actually, if say, let's say that if you have a perpendicular distance of h, you can write the magnitude of the moment can be written as F times h. Okay, that is the rotation effect, and that can also be written as F times R times sine theta. Okay, R sine theta being equal to h anyway. Okay, so this is the moment of a force about a point. Actually, you can also say that this is MO if you like. So this is the concept of the moment. There is another concept called the coupled, which is closely related, of course. If you have two forces, like here, with equal and opposite forces, the distance of them between is h. Now these forces have a couple of m equals F times h, and actually this whole thing can be represented, instead of these forces, we can represent them by a couple like this one. Okay, you don't really have to deal with these forces because, as you see, the summation of forces here is 0. they have no effect on the system except for their couple. They have a couple on the system, but their effect, their total effect is zero. Another important thing is forces have a point of application. Point of application. Okay. Whereas the moments don't have a point of application. Moments have no point of application. In a way, they are called free vectors. Moment is a vector as well, as you know, but it is free. If you have a body like this, the moment you apply can be applied, well, it is on the body, but the location, there is no location, okay? It is somewhere on the body, but you don't have, well, there is no such thing as the moment of this thing about this point, let's say, okay? Moment on rigid bodies are free. You can just relocate them as you like. Okay, just some more review. Adding vectors. Again, things possibly you know, but if the three vectors are the so-called concurrent, what does it mean? They are applied to the same point, or eventually their point of application reaches the same point. For example, if you have a point here, and then say this is F1, F2. This is F3, okay. Three forces act on this body. Their point of application, well, they are eventually coincide at a single point. So what you can do is you can add them up simply by like this, F1. So the resultant is going to be, this will be the resultant force. Their addition is going to be, what will that be? It will be, okay. This will be the resultant force, let's say. Okay. So the R is going to be, R is simply F1 plus F2 plus F3. Now you might think, what else? Okay. Obviously, the resultant is going to be the addition of the forces. Well, the thing is, that's true. The resultant is the summation of the forces. But if the forces are so-called non-concurrent, which means that they don't meet at a certain point, which is also a possibility, right here. Let's say that this is F1. This is F2. Well, two forces always meet at a certain point, but there might be a third force That is totally irrelevant. So these are non-concurrent forces, okay? You cannot make them meet at a certain final point. So you can take a point here in the body, about a point O, let's say. In that case, so this is R3, this is R2, R1. Okay. Well, here obviously still the summation of all the forces is equal to the R. The resultant force is going to be an addition of these all three forces. But there is also these non-concurrent forces are going to have a moment effect. So the moment about point O is going to be equal to summation of Ri cross. Okay. So basically, in this case, this is equivalent to, let's say, supposedly it is the same body. There might be an resultant, like, let's say the resultant is in this direction. But also on top of that, resultant, sorry, the resultant has to be applied on O. Right here, resultant. And also, there has to be a moment, MO. Okay. So these three forces are equivalent to a resultant force and a couple of MO. It's a couple, not a moment. The correct term is a couple. Actually, this can be reduced to another diagram, as you can remember, maybe remember from statics. Say it is the same thing. Let's say this is point O. Here, this is R. It can be reduced to a single force. Let's say that this is RA. The direction is wrong. It has to be in the other direction. Well, you understand the idea, but correct this. Let's say this is point O. This has to be point A. Where MO has to be equal to RA cross width. So this can be the whole forces, non-concurrent forces, can be eventually reduced to a single force acting at a certain point at A. Okay. We can reduce the non-concurrent forces to a single force, taking the effect of the couple into consideration. Okay. The couple effect of the forces have to be equal to RA times R. Let's not spend too much time on this. I suppose you know these from statics as well. So let's go on to what are the forces in machines. Um, there are the external physical forces. This, I suppose, includes the gravity, right? Gravity force, which is, as you know, the mg force. And there might be some external forces acting on the machine. Then there are the joint forces on each member. Another name for this is the reaction forces. Then there is the friction force. And finally, there are the inertia forces, like MA force, okay? Now, if you look at the reaction forces, which I want to look at now, let's say that you have a pin joint, a revolute joint. Um, so, let's say it is something like this. And to this joint, you connect a member. Okay. So this is a R joint. Now, you replace this revolute joint. By the way, no, there is no, we assume that there is no friction on the joint. Okay. In this case, what kind of motions does this joint prevent? Let's take our member on which the joint is applied. It prevents on this joint point, whatever that joint is, it prevents the X motion and Y motions, right? So there has to be a Fx and Fy. So the revolute joint can be replaced by two forces. Because the joint prevents the X and Y motions of the pin point, but it doesn't prevent the rotation, so there is no moment effect here, as you see. As you see, so there are two, let's say, forces acting on the revolute joint. It prevents one motion, sorry, two motions, so there are two forces. On the prismatic joint, on the other hand, if you look at it, let's say that this is your member, and this member is on a prismatic joint like this one. Okay. If you remove this prismatic joint, again, no friction, let's say. This would be moving in the X direction, but it is not moving in the Y direction, okay? Motion in the Y direction is prevented, and also the rotation is prevented. So if you draw the free body diagram without the joint, the forces you have to apply to this joint are, well, there has to be a force preventing the y motion, Fy, and there has to be a force that prevents the rotation, right? Like here. Okay, there has to be a moment effect because this prismatic joint prevents the rotation. Here, the P joint prevents, let's say, y and theta motions. Whereas R joint, R prevents x, y motions. Therefore, you have to include these forces in the free body diagram. If you have a cylindrical joint, for example, which is a kind of a three-dimensional thing, but let me give you that example. So this is cylindrical. Cylindrical joint prevents what motions? It allows you to move in this direction, let's say x direction, and it allows you to rotate in this direction. But all the other motions are prevented, as you see. So the cylindrical joint has to be replaced by, well, kind of four forces acting on it, which will be, let's say, F, that's it. Then there has to be a here my here. Okay. So the cylindrical joint is replaced by four forces in the free body diagram. Well, four forces meaning two forces and two moments, okay? Or force effects, let's see. The free body. Okay. One last thing, let me write it here. There's an empty space here. For the reaction forces, if you have two joints connected to each other like this, let's say this is a pin joint, a revolute joint. Let's say this is ith element, jth element, jth member. As we know, action equals reaction, so Fij equals minus Fji vectorially. So what we have is, if this is our ith element, and if this is our jth element, member, the forces acting on them, the reaction forces, have to be equal and opposite in directions. So if this is Fji, J acting on I, then this has to be, there has to be a minus, well, this will be my Fij, which is minus Fji. And remember that our convention is Fij means force acting on J due to I. This is okay. I think it's time for a break now. Let's stop here for some time. We will continue. Okay, we will be continuing. Let's open a new page. So the forces, we were talking about reaction forces. Now let's look at the physical forces, which includes the gravity as well. What can they be? Physical forces can be, as I have said, external forces. It can be the gravitational forces, which is the weight. Okay. It can be the spring forces, for example, are due to deformation or whatever. Friction is another force. It's a resisting force. We don't classify this as so if you have a external force, if you have an mg here, and let's say that you have a spring here or something like this. Okay, you replace this by external force, the weight, which is equal to mg, and then there is a spring force. That's spring, let's say, in the direction of the spring, for example. And the resisting forces as we have said, are the friction forces, which can be dry friction, the viscous friction, and the Coulomb friction. Okay. The Coulomb friction, you have let's say, the friction forces in the viscous friction is equal to some constant times the derivative of it is proportional to the velocity. Whereas here, this is a little bit complicated. This is the friction force is, well, if there is motion, it is mu n times the sine of SGN means the sine. This is the so-called signum function, which means that so there has to be a minus sign also here. It is opposite to the direction of the velocity friction force. Okay, that's it. And therefore, the dry friction is a nonlinear function of velocity. Therefore, it is more difficult to analyze. But we won't go into that. Let's keep it here. So what do we do with all these forces? We draw the so-called free body diagrams. This is essential in analysis of static and dynamic analysis. So what we do is we replace the joints and the external members by forces. in the free body diagram. Let's say, let me give you an example here. Let's say that we have a prismatic joint and a revolute joint on a member like this one. Let's say that this is member I. Let's say that this is F. This member is J, let's say. Okay. So we have, we are going to draw the free body diagram of the, let's say, for the member I. The free body diagram, you will isolate all the external effects and replace them by forces. The external forces will be here, F. But there will also be the weight of this member, weight. Okay. What else? There is the revolute joint. The revolute joint has to have two forces. Let's put FJI, Y, let's say, this is FJI, X. In the X direction, you have the following. This is due to the revolute joint. Okay. What else? Due to the prismatic joint, you have other forces. Let's put them in some other color. Let's call it G1I. One is the ground, as you see. Let's say this is 1. So the ground applies a force of G1I to this thing. And secondly, there is the moment effect, the couple effect of this thing. So you have M1I active on this. So this is the free body diagram. And although all these forces, if you are making a static analysis, they have to add up to 0. Okay. This is the kind of thing we try to draw. And if you have static equilibrium, this means summation of all forces have to add up to 0. Okay. And the summation of all moments about any point have to add up to 0. Okay. And if you have in 3 dimensions, this gives you 6 equations, as you know. Whereas in 2D, this gives you 3 equations. These 3 equations are, as you know, the forces in the x direction is 0. The forces in the y direction is 0. And moment about some point, it doesn't matter. For the static analysis, it doesn't matter where you take the moments. It's 0. So these are the 3 equations are these. Okay. So, so what we do is we use the free body diagrams and 3 equations for each body. And on top of that, there will be the compatibility equations, like the forces on the connected members should be the equal and opposite, and so on, from which we can solve for our systems, for our mechanisms, the forces in our mechanisms. So what we want to do is to solve for the, for example, the reaction forces, and find out what kind of forces act on each member. In order to make this easier, we have certain, actually, the so-called force members, two force members, three force members, which makes our task a little bit easier to do. If you look at, for example, the first one is the two force member. This you should remember from statics. But let's say that. Anyway, this is well, if you know that there are just two forces acting on a number, how can these forces be? Well, this member is in static equilibrium, by the way. These forces have to be like this. There is no other way to achieve static equilibrium. If this is point A, this is FA, let's say, then if there is another possible force, the other force has to be, FB has to be minus FA. That is, this has to be equal in magnitude, opposite in direction. In magnitude, opposite in direction. There is no other possible way. You cannot have, for example, two forces that do not act on a same line and create an equilibrium on a rigid body. Okay, this is not possible. For example, this one and this one. Okay, FB. This is not a possibility because this cannot remain in equilibrium. As you see, there has to be a resultant force that here in this case, the summation of forces is not zero. Whereas here, the summation of forces will be zero. And the summation of moments will be zero as well. This is also satisfied in the two forces. I have to go through. There is no other possibility. Okay. If there are only two forces acting on a body. So if you have a body like this, what does this mean? L-shaped body, for example. If there is a force like F1 here, the other force coming here should be in this direction, F2, and F2 has to be negative F1. For example, for equilibrium. The second thing is two force plus one couple member, one M member. Now again, these two forces, if you have an object like this, if there are two forces only, I'm sorry, not two forces. Let's say this is FA. And let's say this is FB. And this thing is in equilibrium. First of all, you have to have FA plus FB vectorially must be equal to 0, which means that FB is equal to minus FA, that's for sure. But also, Um, but also you have to have their couple effect, which is the, as you know, the perpendicular distance. Let's say this is h. Uh, there has to be a couple effect here, which is this thing tends to rotate it in the clockwise, so the couple effect has to be counterclockwise. I should say like this. M is a vector. Its magnitude has to be equal to h times a, or h times f. Doesn't matter. So let's say that this is our first equation and this is our second equation. For equilibrium, both 1 and 2 must be you cannot have only one, okay? They have to be both satisfied, otherwise you cannot have equilibrium. So if there are two forces, there has to be an external couple that counterbalances their couple effect, okay? If you want static equilibrium on this body, otherwise you cannot. Well, sorry, it's not possible. The third possibility in this case, you have a rigid body on which three forces are acting. Now, these three forces, there are only three forces. There is no couple on acting here, okay? So the three forces must be, let's say this is F1. This is 3. Now, as you can guess, these forces have to be eventually meeting at a certain point. Let's say this is F2. So you should have F1 plus F2 plus F3 must be equal to 0 vector, okay? And also, forces must be concurrent, which means that meet at a single point. Otherwise, well, it's not possible to have equilibrium. You can also have, well, 3/4 and the moment number, etc., etc. But it doesn't matter really. The thing is the moment about point O of the forces, which is, but obviously you see that it is. In order to have equilibrium, you have to have this. Okay. It is possible to have 3 force and the moment number, 4 force number, etc., etc. But I don't want to go into details of these. At this point, we have done a basic statics review, so we can go on to the static force analysis. Of machines, let's say. Now, our choice, what we want to do is take a mechanism like a 4-bar or a slider crank or something like that and analyze it, the forces. And as we said, we do the static force analysis as a starting point. Eventually, we have to do the dynamic force analysis. Okay. How do we do it? Now, let's say you can do purely analytical analysis. Okay. Actually, okay. I'll explain this. Graphical methods are kind of extinct now. Extinct means something like that. Okay. They are not that much used any longer. Okay. You know, you have to draw things and so on. To a certain extent, they are used, but not much. Actually, probably the best way is to do this analytical plus use graphical insights. We will be such as 2 force plus 1m, 3f number, etc. Now, this will be purely analytical way of analyzing the mechanisms is possible, but it takes a lot of time. It's long, okay? So we won't be using it that much. It is possible. I'll give you one example, possibly. Graphical methods are not that much used, just purely graphical, but we will be mostly using this one, analytical, plus using some graphical insights from the problem. Okay. So let's try to start one example. I don't know if I can finish it today, but let me try. So the example is the following. It's a slider crank. It's a simple mechanism. How is it like? It is like this. You have a Also on top there. So, from moving. So F14 is the external force. And let's say that this is given. The torque T12, the external torque that keeps this mechanism in balance, is what we want to find. What else do we know? We know the geometry, we know the link lengths, etc. So this is theta 1, 2 is known. Is known. Yes. I guess this distance x is known, but it's kind of irrelevant. The distance s. So we want to analyze this. So we want to find T12, but we have to deconstruct the whole mechanism and find out the T12 and the reaction forces. We assume no friction, and the gravity forces are negligible, let's say. So the weights of objects are not that important. So what do we do? Well, we draw the free body diagram of each row, FBD of 2, 3, and 4. And let's do that on the next page. I say this is our link 2. This is our link 3. This is our link 4. We will draw the forces on that. I will first start with the so-called purely analytical method, okay? To show you how it is done. It is systematic, but it is long, as you will see. But what do we know? There is the external torque T12, which we want to find. But now we have isolated these, so there is G12X, the reaction forces G12Y. Okay. Here you have F32X, F32Y. Okay. These are the forces acting on it. This has a length of A2. So these are all the forces. This is force acting on 2 due to 3. This is 3. This is 4. Force acting on 2 due to 3. How about this one? You have F23X, F23Y. Here you have another revolute joint, so F43X. And here you have T4, 3, 4, y. What else? F14, external force, and then the reaction forces. G14. Okay. This is point, let's hold A, this is point B. So these are the forces. Okay. Now for each of them, we are going to write the forces. Let's say for the second one, the forces in the x direction is G12x plus F23, 32. The summation of forces in the y direction is let's call this point over. G12y plus F23y equals 0. And then we have to take a moment about somewhere. Let's take it about point O, okay, which is MO, which is T12. T12 is an external couple. Then you have, well, you have to take the couple of these forces about this point. So this is theta 12, this angle, plus F32x times A2 sine A2 sine theta 12. Okay, that is the rotation effect of F32x. But then F32y has a rotation effect, but it's in the opposite direction. F32y A2 cosine theta 12, 0. So much for the second link. For the third link, you have the summation of forces in the x direction is F23x plus F43x equals 0. Forces in the y direction is F3y. And then we have to take a moment. Let's take a moment about point A. In which case, this has a length of A3. This is theta 1, 2. 4, 3, y. A3 cosine. So we are looking at y, so that will be, yeah, well, where is that cosine? Just a second. 3x. Let me write this down. A3 sine 3 equals 0. cosine and sines for an angle greater than 90 degrees. What is that going to be? Cosine is this. I think if you add 90 degrees to a cosine, what will you get? This is correct, but I just want to confirm that it is correct. You say, if you say that, let's say this is angle alpha, you can write alpha is equal to pi minus theta 1, 3, right? So cosine alpha would be, you can just find it out. It's not that difficult. Cosine pi cosine theta 1, 3 minus sine pi. Example. Sine pi would be 0, right? So this would be done. And cosine pi would be minus 1. So it is minus cosine 3. But its direction is opposite. So minus with a different direction is correct. So it's plus. Let's look at this one. Summation of forces in the x direction, F3, 4, x minus F1, 4 equals 0. Four, minus plus 1, 4, 0. And if you take moments about point B, let's say, M1, 4. Well, let me just do this up. Draw this a little bit better. Let's say this is G14, and this distance is A. So M14 plus G14 times A. This is the point of application of the reaction force. That A distance might not be known, by the way. So we have 9 equations here, as you see, okay, from the free body diagrams. And also we have compatibility equations, actually. Also we have, what do we have? Let me write them here. F23y is equal to minus F32y, okay? F23x is equal to minus F23x. That is the action equals reaction in the joints. F43y equals minus F34y. F43x equals minus F34x. Okay, 4 more equations. 1, 2. These are not minuses, so let me just not confuse you. We have 4 more equations. So in general, we have how many equations and how many unknowns. Let's have a look. We have 9 plus 4 equals 13 equations. And what are our unknowns? Well, C12X, C12Y, C12 F32Y, F32X, F23Y, F23X, F43Y, F40X, F34X, F34Y, that's G14, M14, M14 is not here. And also this A is unknown. So 1, 2, 3, 4, 5, 6. But I think maybe let's say that if I did everything correctly, let me see. Okay, this A has to be, yes, it has to be somehow given, otherwise you cannot really determine. So you have 13 unknowns. 13 unknowns and 13 equations, as you see, which can be solved. It is possible, and actually 13 equations and 13 unknowns, if you have a computer program to do this, it is quite easy to do this, but if you do it by hand, this is too complicated. This is purely analytical method, is too complicated, really. Solving 13 equations with 13 unknowns. Although the equations are easy, mostly very easy, you know, it's a lot of work to do this. Instead, you can simplify this quite a bit by using the fact that there are certain geometric relationships between the elements. Okay, that is, for example, you don't really need to use these compatibility equations, these equations. Then you can directly implement them. Okay, these 4 equations, and then using the fact that some members are 2-fourths members, some members are 2-fourths and a moment member, and some members are 3-fourths members, you can simplify your equations and get a solution very quickly. But since our time is up, I think I will stop here and continue the next time. Okay, so let me stop here.
Hocam,
Yes.
are we gonna responsible from this part on our quizzes?
No.
Okay, hocam. Thank you, hocam. Have a good day.
Mm-hmm.